This is content of part 4a if you're interested only in specific part of this video. Just jump to its start time. Therefore, the data analysis of this measurement and evaluation of anisotropy field is not as simple. To summarize, we need 4 steps. The first step is the subtracting of the component of the Hall voltage, which is independent of magnetic field. The second step is normalizing the Hall angle to its maximum value. The third step is evaluation of magnetic field, which is induced by spin accumulation, by fitting together the left and right parts of measured spectrum and making the dependence of the Hall angle symmetrical. The fourth step is the calculation of in-plane magnetization and the linear fit to find anisotropy field. Additionally, there are many measurement data which needs to process. For example, if we open one file, you can see there are more than 14 measured spectrum corresponding to different values of bias perpendicular magnetic field. Also, there are many files which corresponds to different current or gate voltage, which also need to process. It's close to impossible to do it manually. You need to do it in some automatic or semi-automatical way. That's the reason why I made this program for automatic processing of measured data. Just go to download, click here and download this zip file. Open this zip file and just unzip all this file in directory of your choice. Next, open program Analyze Anisotropy New 2. You can open either executable file or LabVIEW file. I will open LabVIEW file. Before showing you how to operate this program, I will show you what kind of data this program requires. For example, let's go to the wafer named Ha.04a.1st and nanomagnet named Ha.04a.1st. And to sort data, meaning the anisotropy field is measured as function of current density. This all the required data. First, the files whose name started with any. The 00 degree means that the scan is along current, and 90 degree means the scan is perpendicular to the current. M1, M2, P1 mean a different bias voltage. So I can open one file, this for example. The top row a value of the bias perpendicular magnetic field in kilogauss. The left column is the value of scan in plane magnetic field in kilogauss. All other data are measured Hall angle in millidegree for 2 correspondent values of the magnetic field. This file, which name is current, note its name can be also gate for VCMA measurement, is for the current density measured during experiment. Each value of the current density exactly corresponds to the indicated bias voltage. Unit of the current density is milliamp per square micrometer, for example, the first one, correspond to this M2, second one to M1, third one P0, and so on. The current density does not do anything for the calculation of anisotropy. The purpose of this file is to associate each of these measurements to a specific current density. This file, which is started with a loop, a normalization data. Now the normalization data, it is a Hall angle measured in absence of any in-plane magnetic field as function of perpendicular magnetic field. We can open one. As you can, that is a perpendicular magnetic field. That is a Hall angle measured at this value in millidegree. As you can see, the magnetic field changes from 7 kilogauss, minus 7 kilogauss to plus 7 kilogauss and back. We can look for its format. For example, just drag to origin. The Hall angle increases with the increase of perpendicular magnetic field for both polarity. The x-axis is perpendicular magnetic field, let's say Z in kilogauss, and that is the y-axis is measured Hall angle in millidegree. The normalization data should be measured at the same bias voltage as the main data. You see M1 correspond to M1, P1 correspond to P1, and so on. The normalization data were taken from another type of measurement, which I do almost for any nanomagnet I measure. The goal of the measurement is to measure the spin polarization of conduction electrons. Often I call it method number 1. In this measurement method, the external magnetic field is applied perpendicular to a plane and the Hall angle is measured. When the magnetic field is applied, the spins of conduction electrons are aligned along the field, and the spin polarization of conduction electrons increases. Because of the increase of spin polarization, the Hall angle increases. The Hall effect, which is proportional to the spin polarization of conduction electrons, is called the inverse spin Hall effect, or ICHE in short. As spin polarization increases, the inverse spin Hall effect increases as well. That is the reason why the measured Hall angle increases with increase of perpendicular external magnetic field. For the normalization of the Hall angle, it is possible to use this original data, but this data are measured with a better precision using a longer measurement time. So I use this data for the normalization. All this data can be loaded into the program automatically just by referring the directory. Just copy directory name, go to program, paste name here, so the program will read current data. You can see the number of current density is exactly the same as here. Before I will explain to you all the details of this program, I want to show you a conventional two-click data processing procedure by this program. First, you copy-paste your directory of your data here, as we already did. Next, you click this button, Do All, and that is all that you need to do. The program will do all the jobs. You can close the program and go to another program for analyzing the result of fitting of this program. Before you click Do All and do the fit, your directory contains the raw measurement data, started with Hani, current data, at which these measurements are taken, normalization data, started with the loop. Normalization data exactly corresponds to the raw measurement data, M1, M1, M2, M2. Next, I just click Do All. And two new files appear which are started with All. Two files correspond to evaluated anisotropy field, all Hani, and two files correspond to evaluated offset field, all off. 0 degree for the scan along the current, 90 degree is for the scan perpendicularly to the current. If you did only one scan, there would be only two files of corresponding angle. Let's take a look at what these files look like. For example, let's open this one. Again, they are text files and can be opened by any program. The left column is the perpendicular magnetic field, which changes from -7 kGauss to 7 kGauss. Top row is the current density in milliamp per square micrometers. All other data are fitted values of anisotropy field for corresponding current, density, and the magnetic field. We can drag this file directly to the origin program, for example like this. This is the current density. And this is perpendicular magnetic field. So we can plot. The plot is exactly the same as shown here. We can plot simultaneously all the currents. There is a slight difference. It is clear there is a dependency of anisotropy field on the current. Now let us take a closer look at the program and what kind of data we can get from it. At first, we can load any specific file of measurements. So you paste your directory of interest and press here. For example, let's load this file at the bias -1 volt. This graph shows already calculated data of anisotropy field as function of perpendicular magnetic field. This graph shows the offset magnetic field, or the magnetic field created by spin-polarized electrons, again as function of the perpendicular magnetic field. The white line shows the current data, and the red line shows the previous data. Therefore, you can compare two sets of data. For example, let's load another file for different value of bias voltage. For example, this time let's load for bias voltage of +2 volt. Now, the data of current bias of +2 volt shown in white, and the data of previous bias -1 volt is shown in red. The difference is weak, but still there is a difference. It means that the anisotropy field depends on the current. Additionally, it's possible to trace the fitting process. That is a normalization data of the Hall angle versus perpendicular magnetic field. That is a raw measurement data of Hall angle versus the in-plane magnetic field. Actually, versus absolute value of the in-plane magnetic field. The white line is for positive in-plane magnetic field, and the red line is for negative in-plane magnetic field. You can see there is some difference. When offset magnetic field is introduced, the difference between these two curves decreases. This is a calculated mean square difference between these two curves as function of offset field. At offset field equal to 40 Gauss, it has a rather clear minimum. If we subtract Ash offset of 40 Gauss from the in-plane field, both data lines coincide with each other. This graph is the same as this graph, but with offset field. You can see offset field makes the measurement data very symmetrical. That is the first step of data processing when offset field is found and eliminated from the raw data. And the next step, we can recalculate the in-plane component of magnetization from the measured perpendicular component. This is in-plane component. You see it is linear as it should be. In the case, if we would not remove offset field from the raw data, this dependence wouldn't be linear. The dependence is very linear now, it is good. Additionally, the line passes through the zero field, which is also good. The linear fitting of the curves gives a slope and therefore the anisotropy field. I would like once more to repeat the calculation path. At first, these two curves are fitted to each other. As a result, offset magnetic field is obtained. The removal of offset magnetic field from the raw data gives a linear dependence here. The linear fitting of which gives the anisotropy field. Therefore, there are two parameters which are calculated. First parameter is the anisotropy field, and second parameter is offset field. These two parameters are calculated for each value of perpendicular magnetic field. These two curves, this and this, are as a result data. Everything calculated automatically. As you can see, dependence of in-plane component of magnetization on the in-plane external magnetic field is nearly perfectly linear, and the line passes through the magnetic field equal to 0. However, you can notice that there's a very small oscillation on top of it. This graph shows the difference between the raw data and the linear fit. The oscillations are very clear. The amplitude of oscillation very small. It does not exceed 1% with respect to linear fit. I will talk about this oscillation a minute later. Let us come back to the program. It is possible to check the fitting for each specific perpendicular magnetic field. Except these two data, all this data is for one fixed value of perpendicular magnetic field as Z. So by pressing here, you can move through the different value of the perpendicular field and see how the good fit and check the oscillation. The magnetic field is displayed here as 4 kilogauss now, for example. Fit is good in all cases. You can see two fits, for offset field, symmetrizing this one, and for this linear fit, and oscillation as well. If you are interested to see the content and other parts of this video, you can find the links below this video.